Greetings. This is the third lesson in a series of lessons covering the basics of power systems engineering. This lesson is on conversion between the Y configuration of 3 resistors to its delta equivalent and the delta configuration of 3 resistors to its Y equivalent. The configuration of the 3 resistors on the right is called a Y configuration, and the one on the left is called the delta configuration. The idea is that given one configuration, to find the elements of the other so that they are equivalent to each other from the point of view of the 3 points A, B, and C. Once that calculation is done, either one can be replaced with the other without affecting the external circuit to which they are connected. We will look at a circuit on the next slide that clearly shows the need for this type of conversion in calculation of equivalent resistance in at least certain types of circuits. Here we are asked to find the equivalent resistance of the circuit on the slide. This problem cannot be solved using the usual series and parallel combination of resistors. You can see that no two resistors are in series in this figure, and as well no two resistors are in parallel in the figure. You'll notice, however, that there are two sets of Y-connected resistors in this circuit, and those, well, the first one is the one with 10 ohm, 20 ohm, and 5 ohm resistors connected at point O. This is a set of one of the Y-connected resistors, and the other one is the one that is formed by the 25, 5, and 15 ohm resistors connected at point B. Those are the two Y-connected sets of resistors. There are also two delta connected sets of resistors, and those are these three here on top. The 5, the 25, and 10 form a delta connection on the top half of the circuit, and looking at the bottom of the circuit, you can see that these three, the 5, the 15, and the 20 ohm, also form a delta connected trio. Converting any one of these trios to its opposite will allow us to find the equivalent resistance. Once I have covered the conversion between Y and delta and Y, I'll come back to this example and find the REQ, or equivalent resistance. Let's take a look at the conversion of Y to delta first. Given the resistance RAO, seen here on this figure, and RBO and RCO, the resistance RAB, RBC, and RCA of the equivalent delta configuration can be calculated as RAB equals RAO plus RBO plus RAO times RBO over RCO. To see the conversion better, I have coincided the two configurations in the next slide. You can see them on one on top of the other. The top delta resistance RAB, this one, is calculated as the sum of the two resistors that share the two ends of it. Those are the RAO and RBO added together, plus the product of those two same resistors over the third one, which is the RCO. Although I'm not showing it here, but the other two delta resistors are found using a similar formula. Let me just go over those quickly. Let's say we want to calculate RBC now. Given this rule, RBC equals, well, I'll add the two Y resistors that are connected to it, that is two ends. So it would be RBO plus RCO, and then plus a fraction. The numerator would be the product of those two resistors, RBO times RCO, divided by the third resistor, which is, in this case, is RAO. And using the same rule, we can calculate RCA as sum of RAO plus RCO, sum of these two, plus the product of the same two, RAO, RCO, over the third one, which is RBO. Now we'll get to conversion of delta to Y. For this case, I'm going to use the conductance equivalent of each resistance in the delta configuration and calculate the conductances of the equivalent Y before converting them back into resistances. The reason for this approach is that dealing with conductances results in equations that are similar to those we have seen for Y to delta connection or conversion, which makes it easier to commit them to memory. Here is the conversion equation for GAO. So if you look at RAO here, and I want to find it, first I'll find GAO, which is the conductance for this resistor. And once I have found that from this formula, I can invert that to get RAO. Again, putting the two figures on top of each other. This time we have delta elements, and we're going to find from them the Y elements. So the conductance GAO of the Y trio is calculated as sum of the two delta conductors that are connected to it, and those are GAB and GCA, inverses of those two that are connected to RAO, and plus the product of the same two conductances divided by the third delta conductance. So there is a fraction added to those two with the two conductances multiplied by each other divided by the third conductance, which comes from RBC and appears here as GBC. You can see the similarity between this equation that goes from delta to Y and the other equation that shows the conversion from Y to delta. We can write the equations for the other two as well. I might have it on the next slide. Actually, I'm going to write it right here. Here you see the equations for a single conductor, for a single resistor here, and a single conductance here, in each case side by side. But just to show how the rest of them look like, what the rest of them look like, on conversion between delta to Y, I'm going to calculate the other two. So GBO then equals GAB from here plus GBC from here plus a fraction that has those two multiplied each other over the third one, which is GCA. And the other one for GCA is calculated in a similar way. In this example, we are given the resistance of the Y-connected trio of resistors, 10, 5, and 20. We will calculate the elements of the equivalent delta-connected set. Starting with the calculation of RAB, the equation is the one you see here. Substituting for the three known resistances on the right side of the equation, RAB comes out to 17.5. So RAB here is calculated as sum of these two that are on either sides of it plus their product. So it's 10 plus 5 plus 10 times 5 over the third one, which is 20. That comes to 17.5. Using a similar formula for RAB and RBC, those are the, for RBC and RCA, those are the other values for the other two resistors. So we come up with 17.5 for this one, and 35 for this one, and 70 for this one. You see those on this figure. In the next example, I will show the conversion from delta to Y. So here's example 2. The resistance of the delta are given on the figure. We're asked to find the equivalent Y elements. Here's the formula for conversion using the conductances. You see that here. So to calculate GAO associated with this one, you have to remember to invert each one of these before placing them in this formula. So the conductors associated with, if we substitute the conductances in this formula as 1/5 for this one, 1/20 for this one, multiply them together and divide by 1/15 for that one, we'll get 0.4 Siemens. Now by inverting this equation or this value, we'll find the RAO, which is what we're actually looking for. RAO comes to 1 over 0.4 or 2.5 ohms. We'll do something similar for GBO, and it comes to this value in Siemens. Inverting that gives us the value of RBO, 1.875. And in a similar way, we find the value for RCO. So these are the answers in going from delta to Y connection. I'll continue the lesson after a short introduction. My name is Fuad Alvandi. I am a PE in electrical engineering licensed in the state of Maryland. This is the third lesson in a series of lessons on basics of electrical power engineering that I have published on the YouTube. You'll find my name and email address on this page. You can visit my website at the link on this page, own-your-destiny.mylearnworlds.com, and you can find comprehensive modules on important topics in power system engineering at my website there. I will now continue with the lesson by finding the equivalent resistance of the circuit that was shown at the start of this lesson. Here's example 3. As mentioned earlier, we can distinguish two sets of Y-connected resistors and two sets of delta-connected resistors in this figure. Converting any of these to the opposite configuration will make it possible to find REQ, the equivalent resistance. For this example, I'll replace the 3 of Y connected resistors, the 10, the 5, and the 20, with their equivalent in delta. Example 1 has the result of the conversion we're looking for, which I'll reuse here. You can see the result of example 1 on the next page. And here it is directly from example 1. We had a similar Y-connected set of resistors and we converted them into a delta, and those are the values that we found for the delta equivalent. So back here, between the points A, B, and C, we can replace these three by taking them out and putting these resistors in their place between AB, BC, and AC. So between A and B goes 17.5. I'm just going to draw a line instead of a resistor, but this represents a resistance of 17.5. And between B and C, we have 35 ohms. And between A and C, going this way, we'll have 70 ohms. So imagine that these three are gone, the Y's, and now we have those three between A, B, and C. I show that figure on the next page. You see it drawn here. So we have gone from this figure to its equivalent figure here, and you can see that in this way the 25 and the 17.5 are in parallel, and the 15 and 35 are in parallel. So we can find the equivalent of these two and the equivalent of these two, and then add them together because now they fall in series, and take the result and find the equivalent between that result and the 70 ohm to find our EQ. I'll show that on this page. So we'll start with taking the parallel of 17.5 and 25, and that's right here. I've pre-calculated that, and that comes to 10.294, and we'll take the equivalent of the parallel of the 15 and 35 shown here, and that comes to 10.5. Now because this set is in series with this set, we'll just add them here together, and we'll find 20.794 to be the equivalent of this entire branch. 20.794, and this 20.794 ohm is now in parallel with the 70 ohm, and the end result is 16.032 ohms. As I said before, you could have actually done it a little bit differently by taking a delta and converting it to Y, and that would have also gotten you the result. As an exercise, if you should do that one, do it that way. Make sure that you get the same answer as you see here, 16.032 ohms with 5 significant digits. We have reached the end of lesson 3. This is Fuad Alvandi from the educational group Own Your Destiny. I hope to see you in another one of my lessons. Thank you.